In this video, I'm going to do an introduction to one of the most basic concepts of calculus, the derivative. To do that, we want to take a look at the difference quotient, which we've learned about in a previous lesson. So let's suppose we have a graph that looks something like this, and we have 2 points on this graph, and we'll call this point point A, and this point down here we're going to call A plus H, with H being a very small distance between the 2 points. Well, for point A, the function value would be over here on the y-axis, f of A, and the function value of A plus H would be up here, f of A plus H. We then define the difference quotient as being the difference between the function values, f of A plus H, minus f of A, divided by the difference between the 2 points. And so A plus H minus A leaves us with just H. And this is the difference quotient. And we use the difference quotient to do two things. Number one is to find the average rate of change between 2 points. Average rate of change. And this is one of its interpretations. And the second interpretation is that it is the slope of the secant line between the 2 points. And so if we were to draw a line between these 2 points, that would be the difference quotient would be the slope of that secant line. Now remember, the key here is that H is a very, very small number. And so in many of our homework problems, we will usually typically let H be something like, 0.1, or maybe even smaller, 0.01, or even smaller, like 0.001, or even smaller, like 0.0001. H is a small distance. Now, let's just suppose that we want to let H become really, 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 really small, even smaller than these values. The question is, how small can we let H become? So on our graph, I'll try to draw it so it looks somewhat similar. We have our point A and our function value over here. But how small can we let H be as the second point on the graph moves closer and closer and closer as H gets smaller and smaller and smaller? Remember, H is a distance on the x-axis. As this point H gets smaller and smaller, our second point gets closer and closer and closer and closer and closer. The question is, how close can the second point get to the first point? How close can A plus H get to A? And the answer to that is it can get infinitely close to A. So we can bring this second point infinitely close to our first point. And to do that, we use an old friend of ours that we've learned about called the limit. And if we were to take the limit as the distance H approaches 0, now it's never going to be equal to 0. That's the idea behind a limit. It's approaching 0 of the difference quotient. Then we have what is referred to as a derivative. And this is the definition of the derivative. The derivative is the limit of the difference quotient as H approaches 0. All right, so you may be thinking, well, why would we want to do that? Well, one of the reasons that we want to do that is because sometimes we're interested in knowing what is going on not between 2 points on a graph. 2 points on the graph, as we know, gives us average rates of change and the slope of a secant line. but sometimes we're interested in knowing what is going on at a single point, on the graph. So as the second point gets infinitely close to the first one, it gets so close to the first one that essentially we only have 1 point. Now, if h was equal to 0, we would have 1 point, but it never does equal 0. Remember, it's approaching 0. It's getting infinitely close to it. Well, when that happens, we essentially treat it like it was just a single point. And so there are two important interpretations of the derivative. The derivative gives us what we call instantaneous rate of change. Instantaneous rate of change. And by the way, if I misspell anything, don't bother letting me know, because I'm not going to change it. So instantaneous rate of change is change at 1 point on the graph. Change at 1 point on the graph. I'll write that in here. Change at a single point on the graph. And number 2, it helps us to find the slope of a tangent line. Because what happens as the second point gets infinitely close to the first point, that our secant line only touches the graph at 1 point. And so what we have is the very definition of a tangent line. So you remember from geometry that a tangent line touches a graph at a single point. Now remember, technically it's 2 points, but the second point is so infinitely close to the first point that we're treating it like it's a single point. So rather than having a secant line between 2 points on the graph, we have a tangent line at a single point. And so the derivative gives us the slope of that tangent line. So you can see, compare the interpretations. The difference quotient, we find average rate of change between 2 points. So if a question on an exam was to ask for average rate of change, you would use the difference quotient. If it asks for the slope of a secant line, you would use the difference quotient. If, however, you are asked to find instantaneous rate of change or the slope of a tangent line at a point, at a single point again, then you're going to use the derivative. Now, in the next video, I will show you how to use the derivative to find instantaneous rate of change and how to find the slope of a tangent line. The purpose of this video is to just introduce the concept of the derivative as being the limit of the difference quotient as h approaches 0.